Okay, let's move on to parallel resonant circuit. So this is the practical parallel resonant LC circuits, and ideally this could be R, L and C in parallel, like this one, ideal parallel resonant circuit. So to construct a ideal parallel resonant circuit from a practical one, you can understand that we need to make this series component in parallel here, just like this. So we need to make this in parallel, R parallel L parallel C. To do this, we can use our circuit theorems. First of all, we know that initially our circuit was series, just like this one. So this was R and this was L. So you know that the impedance is RL plus JXL. This was RL, and for this L it was JXL. So this was the impedance equation. Now if you write the admittance, then 1 over Z, so it will be 1 over RL plus JXL. Then here actually the calculation was performed from this line. It was just in the numerator we have multiplied by RL minus JXL, and so here RL plus JXL and also RL minus JXL. Then in the denominator we have, and this was just a plus b, a minus b, so a square minus b square formula. So this comes RL square minus JXL whole square. Then j square equal to -1, that's why the denominator appears as RL square plus XL square, just like this one. And then in the numerator we have RL minus JXL, and then if we divide in this minus region, then it will be just RL divided by RL square plus XL square minus J into XL divided by RL square plus XL square. So here this sort of calculations has been done. Then we can also this RL we can put it to the denominator part. So now this is like this, and the second one is like this. So if we convert it to our simplest form, right, 1 over RP, then 1 over J into, let me write it, XLP. So we can write Rp equal to this one, that is RL square plus XL square minus RL, and similarly this XLP will be this one. So our series branch is now converted to parallel branch. So RL and XL was in series, now they are in parallel. So the equivalent form are just derived here. So now we have more of a ideal network. That means we have the resistance, inductance and capacitance all are in parallel. So if we now draw this, so this is our RP, and RP equal to this one, RL square plus XL square divided by RL, and this is XLP, that means this one, and XC was in our previous circuit also. And you know that in case of parallel resonance circuit we generally provide a current source, and for a practical current source we generally have some internal resistance in parallel. So this RS is actually the source resistance, and for current source we generally show the source resistance in parallel with the current source. So this is the sort of equivalent circuit of a parallel resonant condition. Now if we combine those two parallel resistance, since we have a source resistance of RS and also we have another resistance RP, so these two resistance are in parallel, so we them convert it to one resistor, just resistance R. So R will be just the parallel of RS and RP. So you know the formula, 1 over R equal to 1 over RS plus 1 over RP, the simple formula. By using this formula we generally convert this RS and RP to a single resistance R. now we will derive the resonant frequency equation. So first of all, we know that in case of parallel calculations, we generally prefer admittance instead of impedance. Anyway, so for our previous circuits, we can write the admittance, total admittance. We have three branches are in parallel, so 1 over Z1, 1 over Z2, 1 over Z3. So in our first branches we have R, and the second branch was the inductance, that was XLP, and in third branch we have the capacitance as XC. So that's why this impedance equations, one is R, another one is JXLP, and the capacitance for is minus JXC. So in the next line, you know that 1 over J equal to minus J. That's why in the second one it appears as minus J into 1 over XLP, and third one, since it was already 1 over minus J, so that's why this came as plus J. So this is our the admittance equation for our total circuits. And now if we take the J as the common factor as the third and second term, then the equation appears just like this: yt equal to 1 over r plus j into just like this one. Now for the unity power factor condition, we can understand that these two should be equal, or I can say that this equation, this portion should be 0. So when this portion should be 0, in this case only resistance branch presents, that means that unity power factor condition. So whenever we put this condition, then appears XLP equal to XC. So this is quite similar to a series resonance condition, but remember this XLP, within this XLP is a complex, and here if you notice our XLP was generally just like this. So within this XLP some sort of resistance is already present, and this is the series resistance with this inductance. So let's move on. Now if we write this from this equation, if we write for this resonant condition, that is YTP, so at resonant condition these two are equal, so obviously this J into that term will be 0. That means YTP will be just 1 over R. So we can also write the total impedance, that is ZTP, that will be 1 over YT. So YT was 1 over R, so 1 over R, that means R angle 0 degree, and obviously that R was RS parallel of RP. If you remember here, obviously R was also complex one, R was RS parallel RP, where RS is the source resistance and RP was the parallel resistance that was converted from the RL and XL. So far we have completed up to this. Now ZTP, that means our impedance. So this was actually similar to this one, ZTP, already it is written, it is R angle 0 degree. So R, as I already mentioned, it will be RS parallel RP. So also this RP was complex because previously we have that resistance, and this is the inductance XL, and also we have the resistance RL. So then we have converted this series portion to parallel portion, right? So we have converted this series to parallel, from where we have written RP. So obviously RP has equation which was RL square plus XL square divided by RL. So if we put that value, if I show you, this was calculated here. So this one RP. So if you provide this value there in this equation, so now you have the ZTP equal to just like this. And similarly for XLP we have equation of RL square then XL square divided by XL, this one. So as the resonant condition XLP equal to XC, so if we put the value of XLP, now it becomes just like this one. And from where we can derive the the resonant frequency equation. So here if we multiply this XL and XC, then it will be RL square plus XL square equal to XC into XL, just cross multiplication. And then you probably know that XC equal to 1 over omega C, right? And similarly XL equal to omega L. So now this one, then we can cancel this omega, and now this is L over C. So we can write this XL square equal to L over C minus RL square. This term we can take it to the right hand side, so this equation appears. Then we can write also this XL. We know that XL equal to 2 pi F, since it is parallel resonance, 2 pi F L. So it was whole square equal to L by C minus Ri square, right? So then this whole square we can write it to square root on right hand side. So this is written here, and from where we can derive the equation of Fp, that is the parallel resonance frequency. So Fp equal to just 1 over 2 pi L root over Lc minus RL square. So this is the expression of parallel resonance frequency. From where we can also go further. So if we multiply C over L in this portion, so initially it was L over C minus RL square. So if we multiply by C over L, so L over C multiplied by C over L minus RL square multiplied by C over L. Since we multiplied C over L in the denominator, we also need to divide it by C over L. So in the root we have this calculation, then this appears as 1, so this is the 1, and this portion RL square into C by L. So here it is written RL square into C by L, and in the denominator we have C over L, just like this one. And then this C over L we can make this outside of the root, so this will appear 1 over 2 pi L, this one 1 over 2 pi L, then root over C by L, and this portion are separate now. And then here L root over C by L, so you can understand that this L we can write to root over L multiplied by root over L, then 1 root over L can be cancelled out, so total will be root over LC. That's why in the next line it appears as 2 pi root over LC, and this portion is similar. So our final expression is just like this: the parallel resonance frequency Fp equal to Fs square root over 1 minus RL square C over L. So why this is Fs? Because this is similar to the series resonance formula. Previously in series resonance I have derived this Fs equal to 1 over 2 pi root over Lc. So this is the expression for parallel resonance frequency. Now if you notice closely, this portion, that is root over 1 minus RL square C over L, this should be less than 1, right? Here this should be less than 1, so obviously Fp should be less than Fs. Since let me write it, let's say Fp equal to Fs multiplied by, let's say, 0.5. So obviously Fp is less than S, since this portion is less than 1.